All right, maybe we can get started as people are trickling in. We are already 4 minutes past. So let me introduce myself. My name is Gundrala Devender Goud. I go by Devender. I'm an engineering director at Microsoft. And in our group, what we do is we design and develop the hardware solutions. And as a part of hardware solutions, obviously the firmware is the key piece. And I also lead the OSF project, the Open System Firmware, along with Ron Minich from Google. And unfortunately, he couldn't make it this time, but I'll cover for it, for him basically. So what I want to cover this session is how many people know OSF? Like just to get an idea, I can see a lot of people familiar with, but I still want to give a quick backdrop so that people are grounded on what this project is and what we are doing about. And then I will talk about some progress update we made since last time we met in the conference in San Jose. And I'll focus on the work streams we created and updates along with the work streams, and then hand it off to the progress we are making on the Linux side, Linux boot, and at the end I want to reserve at least 10 minutes for Q&A. So that's the agenda. So just to ground everybody, these days the system designs are way too complicated, and there are a ton of firmware in almost in every device you can find. So there's always a confusion, okay, what is this system firmware, and in the context of at least the cloud node, what we have in the hardware. I try to give a highest level picture. So you can see here, you have left side a rack full of nodes, and then the network appliance and the switches and whatnot. And in that, primarily, we are talking about a control plane, like out of band, how do we control this rack so that we can cater for the cloud usage models. And there is a data plane, so that's where the action comes into picture, and that's where the processing in terms of the data processing, compute, storage, whatever the use model is. And if you explore the server node, which is really a data plane, you have some examples I try to give, different types of firmwares inside the node. There is a BMC firmware, there is a devices, the network device, and FPGAs, whatnot, it has its own firmwares. And even the power supply has firmware these days, and plays a critical role too. And then the M.2s and like that. So if you explore the traditional term for the system firmware is the BIOS, the legacy term, but many implementation in different implementation, and one of the key implementation is UEFI. And I try to explore even within UEFI there are so many modules. So hopefully people get a sense what I'm talking about. The system firmware is nothing but UEFI firmware, one of the implementation, and within the rack. So there were a lot of discussions last year when we started on this project. It started as an email thread from Ron and David and Trammell and all. Okay, why do you want to even invest in this, developing something open in the firmware? Today the traditional model is get the code from the IBVs, the BIOS vendors, and then you make your own changes and you maintain it, right? That is one of the, at least my experiences has been, it's a frustrating part, because you cannot innovate in a rapid accelerated fashion, because you cannot check some of the prototyping, some concepts testing and all. So it almost stifles that model, the current development model stifles the acceleration of the innovation in this space, right? So there's a need for making it open. Today it's all closed. And then the second piece is every silicon vendor, when they start off, their boot flows are totally different. So we need to have different answer for each of the boot flows when you try to cater for a complete marker segment, if you are trying to leverage these, right. So there is a need for making it common as much as possible, so that the underlying silicon interfaces are agnostic to the upper layers within the system firmware. And then there is no single answer. Everybody has their own implementation, and Microsoft has own way to implement firmware for their roadmap, and Facebook has their own, Google has their own. There is no, especially the CSPs, the cloud service providers, you can say the complex way to view the system firmware. That's the most complicated one, because you are trying to do a lot of things remotely. It presents a lot of challenges. So everybody has different implementation. So the thinking was, hey, can we come together and do something benefiting each other and make it open, right? And then the other main thing, motivation, is the hardware is accelerating at a fastest pace. I mean, if you go down the hall, you can see a lot of companies. This is one of the conferences. There are multiple conferences in the industry, and even in this conference, you can see a big variation and big innovation in terms of the hardware, right? And then the key piece, the nucleus of all the node, I would say, is the system firmware, even in the boot time as well as runtime. So we need to catch up. So how do we, the new use models, new technologies, we need to incorporate in it, and it's not possible to scale at that level, because there's so many technologies coming, and everybody can take advantage if you try to make it open, and then everybody develops and shares with each other. So that's the motivation, one of the motivation. And in my experience, prior to joining Microsoft, I was at Intel for almost 18 years in data center group. And my experience always in this space is, when I came to Microsoft, I looked at it, it's not cloud ready. I mean, the cloud use models, if you try to configure it remotely and manage it, telemetry, diagnostics, so many complicated things, it's not cloud ready in any fashion. You have to invest a lot of firmware resources to make it cloud ready. But if we can solve it for industry, everybody benefits. So that's the motivation. So truly open solution, I call the hardware plus firmware is together, right? So these are some of the challenges, and how do we address is what OSF was born out of it. And then company leaders came together, and we started discussing, okay, what do we do about it? That's the backdrop. So as I told, there are many implementations, but everybody has a choice of implementations. And as an example, Microsoft is heavily invested because Windows affinity. We have invested heavily into the UEFI path. And then Google, Facebook, and all from the Linux affinity, they have their own implementation. But how can we leverage in this diverged model? How can we converge was a question, right? So we just put together a high level concept. This is nowhere near to any architecture or anything like that. How do we come together to solve this problem was the motivation of this diagram. So you can see here, many silicon vendors, they can supply their silicon interfaces, and then you have a module which we are still in the process of developing, which will help us to go in different paths. So one can go from core boot with Intel's help or AMD's help or anything, the silicon modules, and go boot Linux. And even they can go through Linux boot and boot Windows. And likewise, the reverse is also true. So this picture is just to articulate that it's possible to come together and solve this problem for the industry, right? And what is our mission, like open system firmware, is you can read, but the essence of it is everybody develops different modules, and then which we can cherry pick to create the system firmware for their own use models. And then the major contributing partners in this effort is Microsoft, Intel is a key player, and then Google and and Trammell is sitting here, 2 Sigma, and Facebook, David, so many people coming together and the key contributors for this. And what we said is, okay, we wanted to get started on the development, but can we define some work streams so that the work can proceed in parallel instead of just in being serialized. So we defined some work streams. So okay, that block belongs and somebody is taking on and then developing full-fledged interfaces and the code for that. Example, OpenEDK, Microsoft and Intel together, we own that block. And core boot, David is an expert. And then Linux boot, Trammell, and Chris is not here, but they took on some leadership in different the modules, the work streams. And so far, whatever work we have done since last March when we started this effort, all the collateral and the code links, everything is in that link of the GitHub. Obviously, this presentation gets uploaded later on. We can have those. And what we do is we want to track ourselves the progress and then discuss some architectural issues or any things, the implementation, take feedback from across the board. So we meet a couple of like bi-weekly on cadence, and then you can go to opencompute.org and click on the OSF, and you will find the logistics to join the call. Lately, a lot of companies have been joining. I saw last couple of calls, Lenovo joined, KVM guys are interested and they are joining. And obviously, the key members are already always there, but many people join. And it's not about joining, but understand what's going on. And I'll talk about there are some open modules somebody can take and run with it and then contribute. That's the key, right? So you can contact one of us, and or you can go to OSF. There's a mailing list. You get subscribed and then go from there. So this is a key part. I want to give a progress. This is a snapshot of what we have been doing since last March-April timeframe in different work streams. And left-hand side, you can see the work stream name, and there's a ownership and the key highlights of what progress we made in terms of each work stream, right? So PI, it's a pre-execution module, which is primarily driven by Intel, and from the CPU research, it starts this module. And Intel is obviously they own the silicon, and they are the key contributor for that module. They continue to drive that. And FSP, the firmware support package, which is meant to be, if people are familiar, I'm assuming a lot of you are BIOS engineers or some type of firmware engineers. So if you are familiar with the reference code or the memory reference code or the UPI code, those are packaged into that module, and the interfaces get exposed to the upper layers so that you can do the Dixie drivers and all that. So that's supplied by Intel, and I'm happy to report also there was some disconnect in terms of how the licensing agreement that FSP module somebody can leverage, and Intel, thanks to Intel, lately I think few weeks ago they solved that problem. So now anybody can go take and then incorporate into their for development purpose, they can do that and then contribute back the changes to the OSF. So that was one of the good things we achieved. Core boot, I'm not going to spend time on some of the modules here because we have a full-fledged presentation following this session in the same room from David and also from Google, Chris, and then Trammell. So core boot, especially our David Hendricks from Facebook will cover a full session, what we are doing there. But at least on the OSF calls, I keep getting updates from these guys. They made tremendous progress. We'll touch on it in this session as well. And then the silicon interface firmware module. This is the module, key module where it ties in different paths, boot paths, and this is being developed by Intel. And the key thing about this one is how do we allow different environments coming together through this interface module. So, this is the module where it ties in different environments from silicon interfaces towards the upper layers to boot to the operating system. So, there the key progress, I will have a few full slide on that, I will talk on that. So, Linux boot, as I said, I am not made great progress, stay tuned for the detail in the sessions, upcoming sessions. And then Open EDK, I have a full slide, I will talk about it, they made good progress. And hardware platform module. So, every OCP hardware vendor who is contributing the design, the hardware design to the OCP, they are expected to supply this module, because they are in a best position to talk about what are the key custom interfaces, you call it like SMBus addresses, I2C, GPIOs, how they are routed and whatnot. They are in a best position to really supply that module. So, that is the hardware supplier. As in case of Mount Olympus, we own that, and we already put as EDK 2. And then the bootloader, so this is, we have Windows, we have Linux, we have different bootloader concepts. How does there's not much work to be done here, because it should be agnostic to how it's hands off to the operating system. But still, if there are any custom interfaces needs to be developed, we wanted to invest here. And at least myself, Microsoft, inside Microsoft, we are talking with our OS groups, how we can make this happen, and discussions are just started yet, I mean in the underway. And build tools, so Trammell and his team, they made a lot of investment. Okay, what do we have today? What are the ways we can pass through those to fit into OSF models? And he started discussing with Intel in terms of the feedback and all. Because the Intel supplies the EDK 2, and then obviously on the Linux side there is effort through the open channels. And then the automated test tools, this is another one, IT Renew, which used to be Horizon, now they are IT Renew. They started contributing here along with Google. And lately Lenovo said, hey, we are very passionate about this module, we wanted to contribute. So, that's what the key message I am trying to send here is pick the module or come up with something which you want to contribute in it, and then own it and drive it and contribute. So, that's the thinking. This is not the end of the list, right. So, there are some more innovative things we could do. Telemetry diagnostics, we do not have a owner. This is I highlighted these some of the modules which we do not have owner. The scope of the work here is, okay, you have deployed this solution in the data center, and you are controlling a Dublin data center from somewhere in the other side of the world. How do we interact with that node, right? So, over the rack manager, the control plane interfaces. So, it is useful for diagnostics, it is useful for when there is a fault, how can you get the debug data and whatnot. It is very critical module, and somebody passionate, then we can talk about it. Please join the call and then take it on. And then there was a big feedback in UEFI, the current implementation, hey, it's very complicated in terms of the firmware modules, the variables with different modules and all, we need to have a standardization. And we took on with Intel, and we are working on some proposals with engineers talking to each other. And source code control, GitHub and OCP, Google, they went and created the infrastructure, GitHub based to, by the way, this happened before Microsoft bought GitHub. So, we should chime in there, but that was the good work done by along with OCP Rajiv. Yesterday that guy was presenting. Hardware requirements. So, you can see the variety of hardware being developed. You can see the downstairs. So if somebody wants to contribute to the hardware designs to the OCP, what are the key requirements in terms of some basic requirements so that they comply to OSF. We don't want to develop OSF which again suddenly somebody develops a unique hardware and we don't know how that hardware is laid out, even though they supply the platform module, but there are some modules which interact with that. So we put together some kind of a 3 or 4 pager document to articulate the basic requirements in terms of the hardware interfaces, right. And then the security coding guidelines, and this is one module which we don't have an owner. I know Eagle from Microsoft, one of the directors in security groups is sitting here. So I haven't got chance to talk to him. Maybe there is an opportunity there, right. And AGISA reference code is clearly silicon from AMD, and ARM boot code. ARM implementations are different, but looking at the server roadmap, ARM, it's all boiling down to KVM right now, with Qualcomm gone and other big companies. So KVM is joining calls. We just started, and hopefully they will go full speed. And then even the power architecture, there is a interest from IBM. There are a couple more work streams which I haven't captured it here. But again, the message is, if you want to contribute, come back and then let us know how you want to contribute in different work streams. So this is a slide I want to spend some time to give a sense of the type of progress we made in that module, the highlighted module, the Open EDK Dixie module. So this is the open we are developing along with Intel. The key goal here is we wanted to support multiple silicon vendors and multiple operating systems and have a single code base which supports different silicon vendors as well as the operating systems. So that's a high level goal, and since last time we met in San Jose, we have been assigning resources and developing and making a lot of progress along with the Intel guys. So we met in March and April some time frame. We already uploaded the initial EDK2, which is an open, somebody can download and boot the Mount Olympus hardware straight away without even developing the other modules to the Windows. So that was a concerted effort from Intel and Microsoft. That was good. And then somebody brought up a problem statement. Hey, EDK path takes too much time, and it is, in spite of a lot of optimizations, it was around 30-second boot. So that is way too high for a cloud use model. And I am happy to report that the work between Intel and Microsoft, there is a demonstration right after this. There is a presentation from Sarthi. He will talk more details about how they could cut down the boot time, the warm boot time from 30 seconds to almost 5 seconds, which is pretty cool. And then we have complicated setups, we have variables and IPMI interfaces, all that. How can we clean up the code and make it standard, open standard and all. That's it's work in progress, that module. And then in the cloud use model, at least we should be able to dynamically morph the boot flows by interacting with the node out of band, and that's where the out of band configuration comes into picture, right. So you have provisioned a node for certain use model. Hey, I want to change it, or I want to reprovision it, I wanted to control certain parameters. So that's the module I'm talking about. Make it simple, the setup. There's no setup, there's no human interaction in the cloud use model. It's always remote, and how can we configure that? So that's another work we are targeting. And then so cloud is all about performance, reliability, how do we service it and how do we deploy it, those kind of high level goals. We started performance work with Intel, and some RAS work, the reliability, availability, serviceability work is underway. And firmware security boot, measured signed updates, all those things. And we planned, there is a plan to port that to our OSF tree. We already have those, but how do we make them open and port it to OSF tree, right, and make it available to everybody. So there is some work there. And Cerberus, you might have heard, or you might have joined some of the Microsoft Brian Kelly's talks, and even Eagle presented something. So there, obviously, since still in development mode, but eventually we wanted to open it up, the interfaces, and to the system firmware. And so there is, I think I don't want to steal the thunder from Saradi, but there are some good things happening in the from Intel side. They're trying to support the HTTP boot and then make it better. And so the FSP and binary licensing agreement, which I was alluding earlier in the presentation, where there was a problem, there is a verbiage which doesn't allow the industry players to take it and archive it or use it for their purpose, the FSP module, which is a key module. And we brought it up with Intel, and they solved that problem. So that was good work from Google and Facebook, and twisting Intel's arm and making it better. But Intel is a key contributor, and they are willing to make these things open, right? And it's for their own advantage. So any questions? Maybe we can tackle the questions at the end, but any questions on this slide? We can, okay. So here is the interface module. Not whole lot of work in terms of the code development happened yet, but this is a great progress from Vincent Zimmer from Intel. He's the industry leader in this space, and he's architecting this module, which is a key module which ties in different boot flows, as I was alluding earlier, right. So the key document, we worked through our OSF calls and sessions, and then Vincent is socializing along with Facebook, Google, and different conferences. How do we make this workflow? Right now it's a workflow. We defined, hey, is this the way to do this module? What are the challenges? How do we solve this problem? So the one which I'm talking about, this is in the green silicon interface firmware module. So even though I didn't highlight, but good work has been, we made a lot of progress, but there's a lot more work to be done here to make it truly interoperable between various boot flows, right? And you get this presentation, so you can. So with that, I will transition to Chris and David Hendricks. They are from so Google and Facebook. They will focus on what progress we made in the Linux boot stream. So go for it.
Testing. Okay. Thank you very much, Kandrala. Yeah, those were some very good points mentioned. I'm David Hendricks from Facebook, and this is my colleague Chris Koch from Google. So I'd like to take a moment to riff on a couple points that Kandrala mentioned. He mentioned that this kind of started as sort of an email thread between Microsoft, Google, and the Open Compute project community, and in particular Facebook in our case. It was a very serendipitous time because we all kind of came to the table realizing that the traditional support model for firmware was not necessarily meeting the needs of our large data center scale infrastructures, where all three of our companies have multiple data centers packed with tons and tons of hardware now. And we've all been doing this for a while, so we have multiple generations We have hardware from many different vendors, and that means since firmware is an integral part of each platform, we had many different firmwares and many different headaches. So this is we're really trying to fill in an important void here, because I think traditionally, a lot of the times, a company doesn't necessarily want to invest in firmware development, and they might have servers from one single vendor, and they might not grow big enough to get servers from many different vendors. So it's easy to fall into this trap where you write all of your support scripts, your installers, firmware update scripts, anything having to deal with errors or whatever else you have to deal with firmware. It's easy to fall into this trap where it's very difficult to keep adding support for more firmwares. But as our companies have seen, our infrastructures have expanded so quickly that this was simply untenable. You can do that, for 1, 2, 3, 4 vendors, but when you get up into the dozens of vendors, then you have all these weird, contradictory code paths and things. So we realized that we really needed to open it up and start to play a more proactive role in our firmware development. One great example of this is OpenBMC, which, very similar story to the system firmware. We used to have BMCs from different vendors, and they each had different support models and different scripts, and it was a lot of different headaches. And then OpenBMC is enabling us to unify support that adapts to our infrastructure. So anyway, we're just, and one of the nice things about this project is that we're not necessarily trying to come up with a single implementation that you're supposed to just take and run with. What we're doing is we're developing enabling technologies that'll allow the customer to take all these different devices and integrate them cleanly into their infrastructure. Good examples include the RAS code that Gonzalo mentioned. Things like error handling. What happens if you have a memory error? Do you pause your system and log it, or do you log something to the OS and have the OS handle it, or do you simply ignore it? One of the funny things about memory errors is that traditionally in the business, the vendors don't necessarily want their customers to see the memory errors. But in our case, we want to see all of the errors. So we've had some friction there trying to get the information that we need to make sure that our hardware and our data centers are running smoothly, because it's just gone against the grain of the rest of the industry. And of course, there's a lot of code cleanup. Our code path, our boot path, doesn't necessarily need to be the same as Microsoft's or Google's or anyone else's. And the traditional firmware model is to ship a very general purpose firmware with all kinds of bells and whistles. But to us, that's pretty scary, because any code that's present is, well, first off, it's a source of bugs, but more seriously, it's a potential attack vector. So we want to make sure that our code base is clean and optimized and doesn't contain anything unwanted or something that we don't know about. All right, so with that, some updates on the Linux boot workstream, which is kind of a parallel track that we're working on. It's not totally incompatible with what Microsoft is doing. There are actually some similarities, and even though we're taking different paths, we'll try to converge and cooperate as much as possible.
All right. I don't know how many of you have actually looked at Linux boots. I'm going to do a quick recap of what it actually is, which is on UEFI systems a way to replace some UEFI modules with a Linux kernel. So in the, I'm going to say the easiest version of actually doing this, you compile Linux as a P32 executable, and you insert it as a BDS target to be loaded in firmware. And that comes from the realization that Linux knows how to initialize devices. So some of the Dixies that are actually in firmware, Linux can handle. And some of the other things that are in firmware, like networking stacks, IP, UDP, all these things, are also things that Linux already probably implements, maybe not necessarily in a better way, but in a more open way and more transparent way to you. The other thing that David was just talking about, code paths that different vendors have in their firmware, can be something as simple as the way that boot orders are implemented, and what happens when things fail. This is something that we would like to have to be exactly the same in all of our environments. And if we have the same Linux kernel with the same user space bootloaders in all of our environments, that behavior is actually the same everywhere. But this is not something that you can only do on UEFI, right? You can ask coreboot to hand off to a Linux payload. You can ask uboot to hand off to a Linux payload. The idea isn't really something especially new. It's the original Linux BIOS idea in the pre-coreboot days anyway. Just kind of a take two in a modern world on that. And some of the things we've already talked about is that, yeah, Linux may have some problems too. I think we're all aware of that. But compared to the code in UEFI, it's something we can inspect and look at and update and measure. Besides that, Linux has drivers for almost everything, which makes it probably the perfect kernel to put in firmware to replace some of those drivers. And something that David's going to be talking about later in a talk is that companies like Google or Facebook have a lot more Linux engineers than they do firmware engineers. So this is a way for us to leverage that knowledge that a lot of people already have, rather than trying to find and hire new firmware engineers and to scale that. So kind of where we are today is we support a few OCP boards in our public repo based on the UEFI distribution that's available for those boards. I believe Facebook is going to put out some coreboot code for the ones that are Broadwell DE based as well. And then, of course, you can do this with anything coreboot or uboot compatible. We're also usually happy to try to take a look at your board and prototype things if you're interested in Linux boot. Of course, I don't want to make any promises for real support. The goal is for us to teach you how to do this on your own and to give you the tools to do this on your own.
So just to clarify on something Chris mentioned, so we actually do have the support code for the Wedge 100S and the Monolake upstreamed in the coreboot repository. So Google and Facebook are working pretty closely on this, but even we have slightly different approaches. So for Facebook's side, we're pursuing a coreboot-based approach, but on Google's side, they're looking at a UEFI, an approach that's based on traditional UEFI with parts replaced. So as far as these boards go, they've done a wonderful job at actually supporting pretty much the whole range of OCP server boards for the last few years. Yeah, we're working very closely on this, and also this effort, a couple boards that aren't listed there are actually part of the telecom infrastructure project, which is kind of a sister project to OCP, which is focused on telecom infrastructure rather than our data center infrastructure. And those boards are currently under source mainboard Open Cellular in the coreboot repository, and they include an Intel Atom-based board and a ARM64-based board. So opening up the firmware for us has not only enabled us to help tame our data center fleet, but also machines that are outside of our data center fleet, and not necessarily servers even, but embedded devices too.
Thanks, David. The other thing I want to talk about a little is we try to be agnostic to what you actually put in the user space with your Linux kernel in firmware, and that's because we try to give you all the tools. You choose what to actually use. But I am going to tell you about what we're actually choosing to use, which is a user space based on Go called uroot. Two of the main things that we like about it is that it is easily reproducible without patches to GCC or any other random hacks that you might have to do. And it's also easy cross-compilation. I'm probably going to show you a little bit about that in my talk later today anyway. And then Facebook has come up with a set of Go bootloaders that work pretty well in DHCP environments and a disk booting environment with some TPM support. But part of the point of us writing all this code and making it open source is that you can also take some of the code and, I'm going to say this as an aspirational goal, hopefully write your custom bootloader in 500 lines of Go that will decide whether you're going to end up unlocking some kind of disk encryption or fail to, like if a kernel fails to verify, contact some service to say the server is sad, you need to come fix it. But these are all questions that you might have to think about and actually answer before you come up with a solution for yourself. We would like to not just prescribe one for you. And then, of course, Facebook and Google are currently experimenting with Linux boot. IT Renew, which you can find downstairs, are actually selling systems with it on it. And they, I believe, have a customer, Nexity, that are currently testing the systems as well. So there are multiple players currently contributing and actually making ways to productionize Linux boot right now. And then the last thing I want to tell you about are there's 3 more talks about Linux boot later today. I should have put the times there. I want to say turning Linux engineers into firmware engineers is at 11. Linux boot continuous integration is at 1, and my talk about Linux boot is at 2. So these are talks where you can find out some more details than what I told you just now. And I'm going to thank you for coming and hand it back to Controller.
Thanks. Is it on? Yeah, thanks, Chris and David. That was really good. So stay tuned for the couple more sessions from those guys to give a sense of a little bit more details on what they have been doing. So anyway, I want to wrap it up and open it up for questions. So the call for actions to this audience is basically, as I alluded, there's a bi-weekly call, 10 to 11 PST time, the US time zone. And you can find the dial-in information at opencompute.org. It's always same, so you can dial in and understand more what's going on there. And I would encourage you bring in your challenges. I mean, this is, as I told earlier, the list is what we thought through as a team, but you can always come with some challenges not being addressed. And if you bring it a challenge, you better come with a proposal and contribute. I mean, I'm just joking, but yeah, so we are willing to hear from the industry and contribute to those work streams. It's a great way to let the industry know what you're doing and what you do at company, and a lot of good visibility and help you can seek from the industry. I would encourage invest in this. And looking for owners as some of the highlighted modules. So if you are passionate, interested, come and contribute. With that, so there were some backup stuff which I put, but I think these are all will be, this is a background on how the UEFI firmware progressed and what's the technical, like a lot of good work, and you can see the stability of the transition. There's a lot of equity. I would say, correct me if I'm wrong, Saradi, there are almost 4+ billion devices running on UEFI. That tells how stable the code is. And that's the code base we're starting off with to make it open. So, and then Saradi talks more about the boot flows and all. So with that, let's, I mean, if you have any questions, I have whole team, they can help me answer or I can answer. So, there's a microphone, somebody has any question? Yeah.
In one of your earlier slides, you mentioned one of the line items was tools. Can you tell us a little bit about where that is at and what has been done there?
If we go
yeah, the build tools made progress and identified gaps in current tool chains.
Yes, so maybe Trammell can help answer that question, but I can talk from the UEFI side, yeah.
I think we have a couple build tools at the moment to that can pick apart firmware images and reassemble them with different parts. And I think besides that, you've worked on some stuff, right?
Well, actually, just to elaborate on what Chris is talking about, so Google's approach and Two Sigma's approach is pretty interesting because they've developed these really neat utilities that really leverage the power of UEFI in the sense that it's very extensible. And in their case, they're actually, so the extensible in UEFI has traditionally meant expanding it to infinity. But in their case, they've actually been reducing it towards the bare minimum essentials. And that's something that's really, really cool. I'll let Chris elaborate on that a bit.
Yeah, I guess one of the things we didn't really mention is that some of those OCP platforms we support on UEFI with Linux boot without actually ever having looked at the source. And we've done that by picking apart the firmware images and writing tools that can parse that stuff and put it back together and take out modules and replace them with Linux. And I think with that are going to come a couple more things you can do. I think it's a powerful tool. Trammell, did you want to elaborate?
Yeah, I think he might have some insights into some of the key problems he solved in the UEFI toolchain, right?
So as Chris and David mentioned, we're able to pull apart the firmware. Our initial tools were all written in Perl, and they're pretty hackish. The Google team has been very proactive in encouraging much safer code development, much more rigorous development. So those Perl tools are being replaced with Go, and actually have a little more of a specification behind them rather than just what works with some of the firmware that we've seen. The other major changes that we've been working on are trying to ensure that everything is reproducibly built. So right now, a lot of the tools that we are checking out are building their own cross compilers. So a complete build of Linux boot, I think, has 3 different GCC builds, which is a little excessive for a lot of this. So we've been doing some work to try to reduce that down to 1 GCC build that we can share between the user space, the kernel, core boot if you're using it, and the EDK2 tray. If you are building EC firmware or BMC firmware, there will be an additional ARM cross-compiler required. Right now, there's going to be a talk later on the continuous integration that we've set up. This has been the IT Renew folks have done a lot of work in being able to build and boot firmware on real hardware, and that's been a nice win to be able to ensure that things are continuously working. Can't think of too much else. Happy to take any questions or just hand it back to the presenters.
Thanks, Trammell.
Just one more thing to riff on that. So another important thing is that maybe a year or a year and a half ago, basically the state of system firmware was that you got a blob from some second or third party, and that was it. You couldn't do anything else with it. And then today we have a UEFI implementation, a core boot-based implementation, and kind of a hybrid in some sense where you can actually just check out stuff from GitHub or some repository, run make or some equivalent, and then build a fully working firmware image that you can flash and boot. So that's
huge progress, right?
Yes.
All right, anybody else has any questions? Yeah, sorry.
So we call this as an open system firmware, right? So how much of the whole thing is open versus some binary blobs or?
So, I mean, it's a broad question. We are trying to get to this mission, right? So, imagine in the open world, we have everybody, all the work streams are coming together, and then if one wants to build for their own hardware, they cherry pick which boot path they want, they download the modules, The ultimate goal is then you build it for your own purpose, or you can even port it or add modules to it. That's the ultimate goal. Are we there yet? Yeah, today in the UEFI Mount Olympus, everything is available without this silicon interface modules and all. So it's,
I-
yeah, it is going to be. No, it is, everything will be source code, except the FSP module and the PI module, which are Intel obviously proprietary, but most of it is, our goal is to be everything open source is available, right? It's not binary. Yeah.
Yeah, I think
Yeah.
it's inevitable that some of those early initialization modules are still going to be closed source
Yeah.
and just blobs. But hopefully in the future they can be blobs simply provided by Intel in a way that you can redistribute. Rather than blobs you have to go extract from the firmware image you got from your second or
Yeah.
third party vendor.
You don't have to hack it, you get available readily. So
Yeah, and that's actually a very good point. That's one of the recent things that Intel did was relicense their FSP binary. So now you can check out Core Boot, and Core Boot can check out FSP and just download it, and you don't have to like download blobs from a third-party vendor. That we're still working around a lot of rough edges. Don't get me wrong, but the process has become way simpler. And so we're making progress, and I think that as the large data center scale customers, push on this a lot more and realize, hey, we need more open source in our infrastructure to help us, maintain our own sanity, and demand it from the silicon vendors. We're going to see a lot of these traditionally closed parts start to peel open a little bit, at least insofar as it's possible. I mean, there might be some limits as far as certain proprietary technologies that they just can't open for whatever reason. But we're bringing that to a more reasonable state.
yeah. All right, I already went over 5 minutes. I think it was supposed to be 9:50, but thanks everybody for joining today. So all the information, this slideware will be available in the OCP. And as I said, I encourage everybody to contribute, come to those calls and listen and contribute and take on some challenging modules. Thank you very much.